Hello everyone. Today I'm going to discuss about various types of ions and peaks under mass spectrometry. In this video lecture, I'm going to discuss the types of ions and peaks like molecular ion, fragment ion, metastable ion, multiply charged ion, quasi-molecular ion, base peak, etc. Now we know the theory of mass spectrometry. In mass spectrometer, the molecules in the gaseous state under low pressure at high vacuum are bombarded with a beam of high energy electrons. The energy is about 70 electron volt. This bombardment can first dislodge one of the electrons of the molecule and produce a positively charged ion called as molecular ion, and it occurs in the first step of spectrometer, that is ionization step. So the sample molecule is bombarded with high energetic electron and it leads to the formation of molecular ion with removal of two electrons. We know that in this technique, the compound under investigation is bombarded with a beam of energetic electrons and the molecules are ionized and dissociate into several fragments, some of which fragments are positive ions. Each kind of ion has a particular ratio of mass to charge ratio that is called as M to E ratio. So the molecular ion contains an odd number of electrons, thus it is a free radical or generally called as radical cation. It contains positive charge as well as a radical, so it is also called as radical cation. An electron beam with an energy of about 70 electron volt not only produces molecular ions but also give to the molecular ions considerable amount of surplus energy, which is quite sufficient to break any covalent bond in the molecular ion having about 4 to 7 electron volt potential. Thus, soon after they are formed, most molecular ions undergo fragmentation to obtain the stability because the molecular ion form that are unstable. Fragmentation can take place in a variety of ways depending on the nature of the molecular ion. So let us see the different types of ions present in mass spectrometry. These are the types of ions: molecular ion or parent ion, fragment ions, rearrangement ions, multi-charged ions, negative ions, metastable ions. Let us see these types of ions one by one. First of all, molecular ion or parent ion. When a molecule is bombarded with electrons in high vacuum in mass spectrometer, it is converted into positive ions by loss of an electron. These ions are called as molecular or parent ions, where M, it represents the molecule, and M plus free radical represents the molecular or parent ion. So the ion formed by the loss of one electron, loss of single electron at lowest ionization potential, it forms a molecular ion. The molecular ion represents the intact molecule which has the same weight as starting molecule M, that is less the negligible weight of lost electron. So here M is the neutral molecule and high energy electron about 70 electron volt is bombarded on the neutral molecule. It leads to the formation of radical cation also called molecular ion, with removal of two electrons. Here, these two electrons are nothing but one electron, that is the incoming electron, and one electron is ejected electron. So, M represents the molecule, neutral molecule, and M plus radical represents the molecular or parent ion or radical cation. So, it is the ionization of molecule on electron impact EI process. If we observe, the order of energy required to remove the electron is as follows. Sigma electrons are more loose as compared to non-conjugated pi electrons, conjugated pi electrons, non-bonding or lone pair of electrons. Here, the energy required to remove the electron from sigma electrons, it is higher as compared to the non-bonding or lone pair of electrons. Many of the molecular ions disintegrate at 10 raised to minus 10 to 10 raised to minus 13 seconds to give a positively charged fragment and a radical in the simplest case if some molecular ions remain intact long enough to reach the detector. So that is about 10 raised to minus 6 seconds. Most molecules show a peak for the molecular ion and the stability of which is usually in the order as aromatic molecules show a peak for the molecular ion and it is more stable as compared to the alcohols, that is also more stable as compared to conjugated acyclic polyenes, alicyclics, N-hydrocarbons, ketones, ethers, branch chain hydrocarbons. So if you observe the order, it is according to the stability to form the molecular ion peak. So here the aromatic compounds, it shows the molecular ion peak stable as compared to alcohols. Most molecules shows a peak for the molecular ion and the stability it is in this order. Now these are the characteristics of molecular ion. The molecular peak is observed if molecular ion remains intact long enough at about 10 raised to minus 6 seconds to reach the detector. This peak gives the molecular weight of the compound, and the molecular ion peak is usually the peak of the highest mass number. We should remember the molecular ion peak is usually the peak of the highest mass number. The molecular ion or the radical ion has mass corresponding to the molecular weight of the compound from which it is generated. Thus, the mass of a molecular ion is an important parameter in the identification of the compound. We know that mass spectrometry, it is the most accurate method of determination of molecular mass and its molecular composition. Mass spectrometry, it is a destructive technique of analysis. As the name suggests itself, it gives the molecular weight and also it measures the molecular mass. Hence, the molecular ion has mass. It is responsible to determine the molecular weight of the compound from which it is generated. So, the mass of molecular ion is an important parameter in the identification of the compound. Now, what are the significance of molecular ion? Molecular ion peak gives the molecular weight of the compound, that is, mass to charge ratio of molecular ion is equal to molecular weight of the compound. For example, C2H5 plus, where mass to charge ratio M to Z or M to E ratio is equal to 29, it gives the molecular weight of ethane. Now, the second important ion observed in mass spectrometry called fragment ions. Fragment ions are also known as daughter ions. What are fragment ions? When the energy is given to molecular ion during electron impact, further cleavage takes place and ions of lower mass number known as fragment ions are produced. For example, this one is a molecular ion or radical cation. It leads to the formation of new ions called as M1 plus and M2 plus. These are M1 plus and M2 plus called fragment ions or daughter ions. So the fragment ions are generated by the fragmentation of molecular ion in ionization chamber itself. Here, neutral molecule will be converted into molecular ion first and then further it will be fragmented into daughter ions like M1 plus, M2 like that. This fragmentation it takes place by two mechanisms. First one that is due to instability of molecular ion or radical cation and second one due to energy of ionization potential. Here M1 plus is formed due to instability of molecular cation and M2 is formed due to energy of ionization potential. So we should remember fragment ions are daughter ions are nothing but generated by the fragmentation of molecular ion in the ionization chamber. When the energy is given to molecular ion during the electron impact, further cleavage takes place and that will leads to the formation of daughter ions also known as fragment ions. Next one, rearrangement ions. Rearrangement ions are the fragments whose origin cannot be described by simple cleavage of bonds in the parent ion, but are result of intramolecular atomic rearrangement during fragmentation. Fragment ion formed by intramolecular rearrangement involving migration of hydrogen atoms from one part of the ion to another are also called as rearrangement ions. We will take the example that is Mac-Lafferty rearrangement in next lectures. Mac-Lafferty rearrangement it involves the migration of gamma hydrogen followed by cleavage of one beta bond and leads to the elimination of neutral molecule. So, the rearrangement ions are the fragments whose origin cannot be described by simple cleavage of bonds in the parent ion and these are formed by intermolecular rearrangement simply by migration of hydrogen atoms from one part of the ion to another. These are probably due to the recombination of fragment ions and known as rearrangement peaks. For example, prominent peak in the spectrum of diethyl ether, it occurs at mass to charge ratio 31 and this is due to the ions CH3O plus which is formed by rearrangement of C2H5O plus ions. Now the next multi-charge ions. Sometimes ions may also exist with two or three charges instead of usual single charge in the mass spectrum. These are known as doubly or triply charged ions. They are created as follows. Molecular ion bombarded with energetic electron. It forms the ion having two charges, doubly charged ion. So it is called as a multi-charge ion. But under normal operating conditions, most of the ions produced are single charge. The doubly or triply charged ions are recorded at a half or one third of the mass to charge value of the single charge ions. And the formation of these multiple charge ions is more common in heteroaromatic compounds. They are also common in inorganic mass spectrum. For example, gases such as CO, N2, CO2 and O2 have measurable peaks corresponding to CO2 plus, N2 plus and O2 plus. So multiply charge ions, these are nothing but some double or triple charge ions which are observed in mass spectrometer are called as multiply charge ions that occur mainly in ESI spectrum. Different will be the mass to charge ratio. The peak will be also different. For example, if the molecular mass is 100, then molecular weight is equal to m by z is equal to 100 by 1. That means it is also 100. But if mass to charge ratio we have to calculate and mass z is equal to 2, 100 by 2 is equal to 50. That means peak can be observed at 50. So as the different mass to charge ratio, the peaks observed is also different. So sometimes the ions may exist with 2 or 3 charges instead of the single charge in the mass spectrum, and these are called as a multiply charged ions or multi-charged ions. And they are common in inorganic mass spectrum such as gases like CO, N2, CO2 plus and O2 which have the measurable peaks corresponding to CO2 plus, N2 plus and O2 plus. Next one, negative ions. The positive ions which are predominant in electronic impact ionization because of greater stability, but the negative ions are not very useful in structural determinations. The formation of negative ions it is very rare, but these can be produced in three ways. As we know that in mass spectrometer only positive ions are detected, but these negative ions are rare in structural determination in mass spectrometer, and the formation of negative ions it occurs rarely by these three ways. For example, Ab plus E it gives the formation of positive ion as well as negative ion. Second way, Ab plus the electron, energetic electron. Again, there is a formation of Ab minus species. And the third way, Ab plus E give the formation of positive ion, negative ion, and also the electron emission. So like that, the formation of negative ions, it is very rare and that are not useful in structural determination. Only the positive ions can be determined in mass spectrometer that are only detected. Then the next one, metastable ions. Fragment of a parent ion will give rise to a new ion called as a daughter ion plus either a neutral molecule or a radical. For example, M1 plus gives the formation of M2 plus non-charged particle. An intermediate situation which is possible, M1 plus may decompose to M2 plus while being accelerated, and the resultant daughter ion M2 plus will not be recorded at either M1 or M2 but at a position of M star as a rather broad purely focused peak. Such an ion is called as a metastable ion. Some fragmentation may occur during their flight down the ion tube field free region instead of ionization chamber. These are known as metastable ions. The metastable ion reach to the detector at the masses lower than the actual mass and it gives the broader peak. If we compare the molecular ion, fragmented ions and metastable ions, the molecular ions are most stable ions having the stability longer than 10 raised to minus 5 second, whereas fragment ions are least stable ions and the fragmented intensity in ionization chamber it occurs in ionization chamber only, whereas metastable ions are more stable as compared to fragment ions but least stable than molecular ions. So, metastable ions, it shows low molecular weight and broader peak. They reach to the detector at masses lower than the actual mass and it gives the broader peaks. Fragment of a parent ion will give rise to a new ion known as a daughter ion plus either a neutral molecule or a radical. That is M1 plus gives the M2 plus non-charged particle. An intermediate situation which is possible, M1 plus may decompose to M2 while being accelerated and the resultant daughter ion M2 plus will not be recorded as either M1 or M2 but at a position of M star as a rather broad peak, poorly focused peak. Such an ions are called as metastable ion. Some fragmentation it may occur during their flight down the ion tube field-free region instead of ionization chamber and that are known as metastable ion. Now the nature of metastable ions. Metastable ions have lower kinetic energy than normal ions and metastable peaks are smaller than M1 and M2 peaks but these are broader. Having lower molecular weight but they show the broader peak. These metastable ions arise from fragmentation that take place during the flight down through rather than the ionization chamber. Molecular ions formed in the ionization chamber do one of the following things. First, either they decompose completely and very rapidly in the ion source and never reach to the collector, as in case of highly branched molecular ions with lifetimes less than 10 raised to minus 5 seconds, or they survive long enough to reach the collector and be recorded there having the lifetimes longer than 10 raised to minus 5. As we know that due to the instability, molecular ions will be further fragmented into daughter ions like M1 plus and M2 plus. But some fragmentation may occur during their flight down the ion tube field-free region instead of ionization chamber and these ions are called as metastable ions. Now these are the significance of metastable ions. Metastable ions are useful in helping to establish fragment roots and metastable ion peak can also be used to distinguish between fragmentation processes which occur in few microseconds. Now, here are some points to remember. In some cases, the base peak is the molecular ion peak, but in most cases, it is different from that of the molecular ion according to the relative stability of ions during fragmentation. Then peaks are commonly observed at mass to charge values 1 and 2 units less than the mass to charge values of the carbocations because the carbocations can undergo further fragmentation by losing one or two hydrogen atoms. For example, CH3, CH2, CH2 plus having the mass to charge ratio 43. Whenever the hydrogen abstraction occurs that leads to the formation of molecular ion having mass to charge ratio 42 and again whenever one hydrogen will be loose we get the new molecular ion mass to charge ratio 41. So peaks are commonly observed at mass to charge values 1 and 2 units less than the M2Z values of the carbocations because the carbocations can undergo further fragmentation only by losing one or two hydrogen atoms. Small peaks that occur at M2Z value 73 that is known as M plus 1 peak to indicate that it is one mass unit greater than the molecular ion M plus, and the M plus 1 peak appear because most of the elements have more than one naturally occurring isotope. Here are some relative abundance of different isotopes. If you observe this table, we get carbon isotope having the relative abundance 100 and the carbon 13 relative abundance 1.11, whereas for nitrogen 14 100, nitrogen 15 0.38, 1H 100, 2H 0.016, like that. So these are the relative abundance of different isotopes. From this table, we get that for carbon, hydrogen, nitrogen, and silicon, the principal heavier isotope is M plus 1, whereas for oxygen, silicon, sulfur, chlorine, and bromine, the principal heavier isotope is M plus 2. For F and I, for fluorine and iodine, there is no heavier isotope. That means do not affect M plus 1 or M plus 2. So these are the relative abundance of different isotopes. We get the values of relative abundance for carbon, hydrogen, nitrogen, oxygen, silicon, or sulfur isotope. We know the mass spectrum. The mass spectrum, it is a graph of relative abundance of each fragment plotted against its mass to Z value. Because of the charge Z is equal to plus 1 for all fragments that reach the collector plate, so the M to Z value express the molecular mass M of fragments. Remember that only positively charged species reach the collector, and the mass spectrum is usually published either as a bar graph or in table form. Note that peak with the highest M to Z value in the spectrum is due to the fragment that results when an electron is knocked out of a molecule of the injected sample. That is, it represents the molecular ion of the studied compound. Thus, M to Z value of molecular ion gives the molecular mass of compound. Since it is not known what bond loses the electron, the molecular ion is put in brackets and positive charge and unpaired electron are assigned to the entire structure. The convention for drawing specifically the molecular ions of molecules containing an oxygen, a nitrogen, a double bond, or an aromatic ring is to localize the odd electron and the charge, and also the square bracket for benzene or only in one partial square bracket and place the odd electron and the charge outside the bracket. Then next point is peaks with the smaller M to Z values known as fragment ion peaks, called as a fragment ion peaks, that represent the positively charged fragments of the molecule. We have already studied what are the fragment ions and how these are formed. These are formed only due to the instability of molecular ion. Molecular ion further fragmented into new ions called as the fragment ions or daughter ions. Next one, base peak. What is base peak? Base peak is the peak with the greatest intensity due to its having the greatest relative abundance. The base peak is assigned a relative intensity of 100% and the relative intensity of each of the other peak is reported as a percentage of the base peak. So, the most intense or tallest peak in the mass spectrum is called base peak. It is due to the greatest relative abundance. We should remember that the base peak will not molecular ion and always molecular ion will not be base peak. So base peak is the peak with the greatest intensity, the most intense or tallest peak in the mass spectrum. Next one, the mass spectrum, that gives us the structural information about the compound because the M to Z values and the relative abundances of the fragment depends on the strength of the molecular ions bonds and the stability of the fragment. So already we have discussed about the different types of ions. One of the ion is also known as a quasi-molecular ion, that is a protonated molecular ion, or the ion which is formed by the removal of one hydrogen atom from the molecule, that is known as quasi-molecular ion, that is M plus H plus give the formation of MH plus, that is M plus 1. It will lose one hydrogen, so ultimately we get the formation of such type of the ion, that may be M minus 1 or M plus 1. A protonated molecular ion, or the ion formed by removal of one hydrogen atom from molecular ion, known as quasi-molecular ion. Now these are the different types of the peaks observed in mass spectrum. First one, base peak, the most intense peak in the mass spectrum called as a base peak. The base peak is the highest peak and it is assigned a relative intensity of 100%. Second one, molecular ion peak. The ion formed from a molecule by removal of one electron of lowest ionization potential, known as molecular ion. Next, fragment ions. The ions produced from the molecular ion by cleavage of bonds are called fragment ions. Next, metastable ions. Mass spectrum of molecule, it shows sharp peak at M to Z integrals, but some show diffuse, broad, low intensity peaks at non-integral M to Z values. These are called as metastable peaks or metastable ions. So if you observe this spectrum, this is the mass spectrum, that is nothing but on the y-axis relative abundance and on the x-axis M to Z values. So these are the fragment ions. This one is the base peak and it is the molecular ion peak. So we should remember that always base peak will not molecular ion and always molecular ion will not be the base peak. So in today's lecture, we have studied the different types of ions and different types of peaks under mass spectrometry. In next lecture, we will discuss the fragmentation of ions in detail. Thank you.